Well, to continue with our discussions on non-ideal solutions, where I had ended the last class was I had told you that usually, since it is very difficult to have a proper equation of state to predict the behavior of real solutions. So, therefore, usually the gammas, they are predicted from empirical or semi-empirical equations, and the simplest empirical equation which is used is known as the Margulis 2 suffix equation, which gives you G by RT in this particular form, and from there we find out that more or less my ln gamma 1 and ln gamma 2, they can be represented in this particular form. G E by RT, this is equals to A x 1 x 2, and from there if we are finding out ln gamma 1, which is nothing but G I bar E by RT, which is del del n1 n1 plus n2 G E by RT, and if you differentiate it, you find that ln gamma 1 equals to A x 2 square. Similar way, you can either differentiate it in terms of n2 and find out ln gamma 2, or you can use the Gibbs-Duhem equation once you know gamma 1 to find out gamma 2. The choice is yours, you can do either of them, and we find that ln gamma 2 is equal to A x 1 square in this particular case. And we have also depicted the curves of excess Gibbs free energy of a solution as a function of composition, and also the ln gamma 1 and ln gamma 2 as a function of composition. And I had already also mentioned in the last class that although the 2 suffix Margulis equation, it is good for very simple spherical molecules, similar type of attractions, etc., but for most of the cases we need to modify this particular equation in order to incorporate the non-ideal behavior of solutions. Now, what are the different ways by which it is done? One particular way was proposed by Redlich and Kister. What they have done is they have simply extended the number of terms here, if you observe. For this case, if you observe that the first equation or the first term, it represents the 2 suffix Margulis equation, and the other terms, they are just the series expansion in x 1 minus x 2. These are introduced. If you observe closely, you will find that it has got some similarity with the virial equation of state modifying the ideal gas equation, and depending upon the complexity of this situation, we can keep on increasing the number of terms in this particular case, and in that way the number of parameters to be included in the model, it depends upon the complexity of the solution. And if you observe these terms, you find that the A, it is symmetric in x, just the A of the 2 suffix Margulis equation. B, if you observe B, it is actually asymmetric in x, and it tries to skew the parabola either to the left or to the right. And if you observe the third term, you will find it is again symmetric in x. What it tries to do, it tries to either sharpen the parabola or it tries to flatten the parabola. So, in this particular way, the contribution of the first 3 terms A, B and C of the Redlich-Kister equation is shown in this particular graph, where we see that the first term, it is the contribution to excess Gibbs free energy due to 2 body interactions of molecules of unlike components, and the second and third terms, these are the second and the third terms, they refer to the 3 body interactions of unlike molecules, right. And so, therefore, if we have expressed G by RT by this equation, the activity coefficients can automatically be expressed in the way we have shown, and from there we can express ln gamma 1 by gamma 2. We can express this by dividing one with the other. This ln gamma 1 and ln gamma 2, it can be expressed in this particular equation, and we can subtract the 2 and we can find out how we can express ln gamma 1 and ln gamma 1 by ln gamma by 2. This can be expressed as A into x 2 minus x 1 plus B 6 x 1 x 2 minus 1 plus C x2 minus x1 into 1 minus 8 x1 x2 plus so on and so forth. And all these terms A, B, C, they are temperature dependent adjustable parameters, because we need to know that the composition dependence of gamma, that should be a function of temperature and pressure. Since it is a liquid phase property, it should not be a very significant function of pressure, but it should be a significant function of temperature. So, therefore, this A, B, C, they are temperature dependent adjustable parameters to be determined from experimental data, right. So, therefore, we have some experimental data on the real liquid solution from which we can depend them, and the number of terms which we need to include, as I have already said, that depends upon the complexity of the solution. So, in that particular way, we find that the Redlich-Kister equation, it is quite flexible and it can adequately represent the excess Gibbs free energy of the solution. We just need to include more and more terms if we have to make it more complex, or rather when we have to deal with more complex situations. Now there is one other way also apart from the Redlich-Kister equation, it is the Hol's equation. This Hol's equation also, it takes into account the two body and the three body interactions, and it gives us some type of rather it helps us to predict the excess Gibbs free energy of a binary liquid solution by taking into account the three body and two body interactions between the like and the unlike molecules. As we have shown here, this first term takes into interaction the two body interactions, and the subsequent terms they take into account the three body interactions in this particular case. Now, based on all this, we find that several algebraic equations have been proposed to determine activity coefficients. Since from thermodynamics, it's rather there is insufficient guidance to formulate unique relationships between gamma and x. So, therefore, large number of algebraic equations are proposed which satisfy Gibbs to Hem equation. They are thermodynamically consistent and they are used, or rather they are just a correction to the 2 suffix Margulis equation in order to predict gamma under more non-ideal conditions. For very less non-ideality, 2 suffix Margulis equation is fine. When we have to go for much further, rather when there is greater amount of non-ideality, we need little more equation. The most generalized formulation to predict non-ideal behavior has been proposed by Redlich-Kister, and Hole has also proposed and both of them they have considered 2 body 3 body interactions, and they have tried to propose that we find that apart from that, if we use some algebraic equations which are basically empirical equations, they do not have much thermodynamic foundation, but they are found to be thermodynamically consistent, number one, and they subscribe to the limiting conditions which I have mentioned, then in that case those equations they are usually used for finding out the activity coefficient. The most common equations which will be important for this particular thermodynamic course are the 3 suffix Margulis equation and the Van Laar equation. These two equations, they are the most common equations where the Gibbs free energy, excess Gibbs free energy model is given by these equations, and the ln gamma 1 gamma 2 expressions are given from here. Now, apart from this, we find that these equations they are fine, but they do not incorporate the temperature dependence of gamma. So, therefore, in order to incorporate the temperature dependence of gamma, we have some more equations which have been suggested. For example, Wilson equation is one where the adjustable parameters in this particular case, the gamma the lambda 1 2 and the lambda 2 1, they are functions of temperature. And we find that this particular equation, the Wilson plot, this is very good for mixtures where the components differ from each other in molecular size and the interactions between the like and unlike molecules are different. So, we find that the Wilson's plot, I will just like to tell you that for this class the 2 suffix Margulis equation, the 3 suffix Margulis equation as well as the Van Laar equation are important. For the other equations you need not remember the equations, but under what conditions those equations have been proposed, that you need to remember, because in future if you are supposed to deal with non-ideal solutions, it is important that you actually know that for which conditions which equation is applicable. But along with that also remember that till today also several equations are being proposed to predict the excess Gibbs free energy and the activity coefficients of non-ideal solutions, because it is very evident that suppose we are working with a mixture of hydrocarbons, we find one equation is applicable, definitely the same equation will not be applicable when we are working with aqueous solution of organic acids. So, naturally with each different compound or each different components of the solution, newer and more different equations are necessary, because all of them finally boil down to the intermolecular interactions and the molecular shapes and sizes which are different for the different cases, right. But again I repeat, I will just be discussing under what condition the more complex equations are applicable, but for this particular class we will be dealing with just 3 equations, the 2 suffix Margulis equation, the 3 suffix Margulis equation as well as the Van Laar equation, fine. So, for most of the cases which are required for you, these 3 equations are fine, but it is important to remember that they do not, or rather they do not express the constants as temperature dependence. For them the same particular constants of the equations are applicable no matter or at what particular temperature and pressure conditions that we are working, fine. So, therefore, in order to incorporate the temperature dependence of activity coefficients, we need to go for more and more complex equation. One such equation is the Wilson equation, where we find that the Wilson equation, it is applicable for 2 conditions. One is the components differ from each other in molecular size. And secondly, interactions between like and unlike molecules are different, right. For these 2 conditions more or less they are applicable, because the lambda 1 2 and lambda 2 1, they are related to the pure component molar volumes and characteristic energy differences, etc. So, therefore, their advantage is, the third advantage is it predicts temperature dependence of activity coefficients gamma 1 and gamma 2, and therefore, these are developed through considerations of molecular behavior. The only disadvantage which has is it is not applicable to systems where ln gamma exhibits maxima or minima. This particular aspect we will be dealing separately after we have finished dealing with the normal situations, and it is also unable to predict limited miscibility. These are the drawbacks of the Wilson plot. Well, other than that, what do we have? We have a 4th suffix Margulis equation which tries to modify further the 3 suffix equation by incorporating, it's basically a Redlich-Kister equation which has 3 instead of 2 terms, it is evident. Then we have a non-random 2 liquid equation, the NRTL equation. This is applicable to partially miscible and completely miscible systems, and in this particular case also we find that here we do not have much advantage over the Van Laar or the Margulis equation for moderately non-ideal solution, but it represents the excess Gibbs free energy of strongly non-ideal and partially miscible solutions quite satisfactorily. After that, we find that apart from these, there are some other equations also which are which have been proposed. For example, we have the UNICAC, which is nothing but the universal quasi chemical equation, and these equations we find that in fact they have been developed by Pruschnitz. He was one of the contributors to this equation. We find that it primarily comprises of a combinatorial part and a residual part, and we find that the combinatorial part, this accounts for the compositions, the size and shape of the constituent molecules. So, the combinatorial part, it basically it comprises of pure component properties only, and the residual part, if you see, that accounts for intermolecular forces and it contains two adjustable parameters. And after that, we find apart from the UNICAC equation, there are also some other types of equations which have been proposed. They are known as the group contribution method. What are these group contribution method? See, if you assume that each particular component of the solution are made of individual molecules, then there are a huge number of molecules, and then for each particular solution you have to find out the how the non-ideality is coming into picture. Other than that, if you assume that each particular solution is made up of a number of radicals or a number of groups of molecules, and it is the contribution of the groups which lead to the non-ideality of the solutions, then in that case you can have a large number of solutions which have the same type of groups. For example, methyl group can be present in a large number of liquids, or maybe the acetate group can be present in acetic acid in a large number of acetates, and we assume that the behavior of these particular groups, they are independent of the behavior of the other molecules. So, therefore, in this particular case, the advantage is if you know the group contribution for the group existing in one solution, you can safely assume that this particular group contributes in a similar way when it is in an environment of some other type of molecules. So, therefore, the other way of finding out or evaluating the activity coefficient, this is known as a group contribution method, right, where we assume that each component it is made up of not only individual molecules, but different functional groups, like say the functional groups can be each particular component of the solution are made up of functional groups like CH3OH, etc., etc., and then a solution of the component is treated actually as a solution of the groups, and then the gamma i's, they are determined by properties of the functional groups rather than the properties of the molecules. So, this is the basic idea, that we have several thousands of chemical compounds, but there are very few functional group constituting these compounds. So, that the gamma in large number of solutions, the basic idea is that the gamma in large number of solutions can be calculated from parameters characteristic of functional groups, and the only assumption here is that it just assumes, the only assumption here of the group contribution method is that contribution of one functional group in a molecule is independent of that made by other functional groups, right. So, therefore, on this basis it's expected that this makes our life little more simpler, because if we know the contribution of one functional group in any molecule, we can safely assume that the same contribution is made by the same functional group in a different molecule. And there are two models which use this particular method. One is the analytical solution of groups, which is known as the ASOG, and it is the unique quark functional group activity coefficient, or it is known as the UNIFAC. So, therefore, I would not like to go into much details of these particular things. It is just important for you to remember that the large number of different algebraic equations, large number of models which have been proposed, the primary reason for the huge number of models are that it is very difficult to use one particular model for the wide range of solutions that we have, considering the different shapes, sizes, orientation and the intermolecular interactions between the different molecules constituting the solutions. And it is important to remember that maybe one particular molecule, it behaves in one particular way in an environment and behaves in a completely different way in a different environment. So, therefore, depending upon the conditions, different equations have been solved and have been proposed, and when we find that the molecules are not completely randomly mixed, possibly due to hydrogen bonding etc., then we go for the NRTL. When we find that gamma does not remain constant with temperature, so in that case we should go for Wilson plot etc. But again I repeat that despite the large number of models which are present, for your particular case you will be primarily concerned with 2 suffix Margulis equation, 3 suffix Margulis equation and the Van Laar equation. So, before I end this class, I would like to discuss the estimation of gamma from using the 2 suffix is very simple, using the 3 suffix and the Van Laar equation. For that, what we do, we try to arrange the equation in such a form that it gives us very simple, or rather the method of solution becomes very simple. So, I would like to discuss this particular method of solution before I end this class, so that if you are given some amount of data, thermodynamic data, say at a constant temperature, usually the data are given as x or y or x and y at either isothermal conditions or under isobaric conditions, right. And you are required to test the thermodynamic consistency of data, or suppose you have data at one particular temperature or one particular pressure, you are required to generate the whole set of data or the whole set of gamma data for the solution, with the compositions varying from almost 0 to, or x1 varying from 0 to 1. These are generally the type of problems that you are supposed to deal with, right. So, for that case, what do? We are going to take up the Van Laar equation and Margulis equation and discuss the method of solution. So, let us take up either of the equations and see in what way we can express it. For example, suppose we are taking up the Van Laar equation. What is the equation? If we write down the equation, we find ln gamma 1 is, say suppose I have, you can, since they are constants, you can express them in any particular way. There it can be a, b, it can be a12, a21 etc. For my case, what I do here is, I have expressed Van Laar constants as b12, b21 and the 3 suffix Margulis constants as a12, a21, just to differentiate that they belong to constants for different equations. So, the Van Laar equation is ln gamma 1 is 1 plus b12 x1 by b21 x2 whole square, right. Ln gamma 2, this is nothing but b21 by 1 plus b21 x2 by b12 x1 whole square. Let me see the 3 suffix Margulis equation. Ln gamma 1 x2 square into, say, a12 plus 2 into a21 minus a12 into x1. Ln gamma 2 equals to x1 square a21 plus 2 into a12 minus a21 into x2, right. Now, if you observe these two equations, what do you find? You find that for this equation, if we write it down as ln gamma 1 by x2 square, this becomes a12 plus 2 into a21 minus a12 into x1. Similar way, ln gamma 2 by x1 square, this becomes equal to a21 plus 2 into a12 minus a21 into x2, sorry, into x1. Fine. So, therefore, does it not imply that if I have a plot of ln gamma 1 by x2 square versus x1, then in that case it should be a straight line, and that particular straight line it should have an intercept of a12 at x1 equals to 0. Fine. So, therefore, from this particular straight line I should be in a position to find out this. Similar way, I can also plot ln gamma 2 by x1 square as a function of x2, and I can also generate a straight line. From this straight line, from the intercepts at x2 equals to 0 and x2 equals to 1, I can find out a21 and a12, right. So, in this particular case, what do I find? That at x1 equals to 0, my intercept is a12, and at x1 equals to 1, my intercept is a21. In this case, we find that at x2 equals to 0, my intercept is a21, here my intercept is a12. Agreed. So, therefore, we find out that from here, if we have data at one particular temperature or pressure, x data and gamma versus x data, then we can very well plot a straight line. From the intercepts, we can find out a12, a21. In a similar way, we can also arrange this particular equation. Just observe this equation and try to find out in what way can we arrange this equation such that from such simple geometrical constructions we can find out the constants b21 and b12. We are going to discuss it in the next class, but before the next class, try to think out how we are going to express the Van Laer equation such that we can have such a simple geometric form, from where just by construction or just by plotting one parameter against another, we should be in a position of finding out the constants of the equation. This is first thing I want you to think. The second thing is, suppose we are using gamma 1 and gamma 2 and plotting in this particular fashion, then what do we find? This equation is going to give me one set of a12, a21. This graph is going to give me another set of a21, a12. How to combine the two and how to find out the average values that should be used. So, with these two assignments or these two thoughts or these two topics for you to think, I end this class. We are going to discuss about this in the next class. Thank you very much.